Hey guys, welcome to Civil Engineers Adda. My name is Abhishek Kamdol Shetter. I'm Tech Structures. So today I'm going to explain you and demonstrate you how to uh, carry out the impact resistance of a plain and rubberized concrete containing steel and polymorphine hybrid fiber. So I have selected this topic based on the paper selected here. Okay, there's a paper here that is what I've told now, just impact resistance of plain and rubberized concrete containing steel and polyfrene hybrid fiber. So in this, let me brief you what is there in this paper. So in this paper, what they have done is, there are two, let me take the highlighter here. Okay, so in this paper there's a plain and rubberized concrete, means the concrete is mixed with it's plain concrete, and one more is a rubberized concrete containing steel and poly polypropylene hybrid fiber. Okay, so polypropylene hybrid fiber. So let me take you down here. So let me take you down. So these are the materials that they have used. These are the first one, appearances of PP, means polyframe fiber, and MS. Okay, then so you can just see the things here. So when you go very detail into the paper, then you'll understand the material specifications there. This one, what you can use, the what all they have used. But here just I want to make you sure that here there's an impact, there's a test setup here. So there is a, we have to cast a beam, here. So let me take, okay, so we have to take model a beam. So we have to model a beam in the Ansys here. I'm just evaluating these results through Ansys. We have to model a beam. The sizes of all them have been mentioned here. And now we have to give a repeated impact load of 4.54 kg with a drop height of 400 mm. Okay, with the drop height of 400 mm, we need to give it impact. Okay, several times we have to impact it several times until we get the first, means we are going to evaluate at what number of blows we get the first crack, and at what number of the load we get final crack, means before failure the final crack, at what load we are going to get. Load in the sense number of blows. We are going to decide the number of blows. Based on the number of blows we can understand the capacity. Okay, the capacity of the band. And one more thing, very important thing, is it is a very low velocity impact. This is a very low velocity impact. Okay, low velocity impact test. This is a very low velocity impact test. Keeping that in mind, we have to you can just see the failure pattern of the specimen after failure. Okay, so now we'll just go to the results and discussions here. We'll just see what is required actually. Okay, now I'm just going to tell you here is what I'm going to tell you here is yeah. So yes, the drop hammer impact test results of plain and rubberized concrete are as follows here. So what is this PC? PC in the sense is plain concrete. So PC means plain concrete. Okay, it's a plain concrete, and RUC1 itself is rubberized concrete. It's a rubberized concrete. See, just you can see here number of blows. So these are all the experimental results. You need to validate that in any simulation software like FEA software, like you can use for Abacus and Ansys. Since I'm using Ansys, so I'm just going to demonstrate it in Ansys. So number of blows for first crack. For first crack, the number of blows for the mix PC1 is 3 number of blows are required for the first crack, and for the complete failure of the specimen we require 5 number of blows. So they have done the average number of blows. The impact energy is 48.1 joules, and total failure is 80.2, means almost we can say it's like 90% of 90% increase. So average impact energy and impact ductility index, so all those things have been calculated. So similarly, they have carried out the tests for 6 specimens for the plain concrete, and some 6 samples specimens for the rubberized concrete. So here is this is a brief, very brief summary, or the abstract of the entire paper here. So now what is the conclusion? By increasing the polyframe fiber content, okay, so all those things have been just noted down here. I'm not going very detail in that because it will take a lot of time. So now what I'm going to do is, my dear friends, I'm just telling you this and this video, okay, this video what I'm going to present is divided into has been divided into 2 parts. I'm just dividing it in 2 parts. First part is modeling, like modeling. First part is modeling. Second part is getting setting up. Okay, it is a setting up of what do you say, the test impact, setting up of impact test, and this is a 2 parts, and we have to analyze analysis in Ansys workbench. So, and one more part that I'm going to divide here is that the second part will be the crack. Okay, crack growth, the growth of the crack, and crack growth and number of blows. Then here we are going to see the impact energy validation. Okay, impact energy validation. So these things we are going to see as first video, the part 1 modeling. There will be setting up of impact energy analysis in Ansys workbench. Okay, so this video is one of the, it will be the best video in the entire YouTube setup here, because the people here don't explain completely with the paper, with the actual paper. They don't completely explain the procedure to carry out the analysis. So many people just carry out the simulations directly, or just they produce the results or the last conclusion. So I thought of making a video on this topic here. So please be patient, and this video might go for a little bit longer duration, since I'm going in detail for each and every part. So guys, so let's start. Let's see the specifications. What I'm going to just highlight the specifications is the specimen. Okay, so it's very okay. So the specimen size here is, specimen, okay, the beam specimen size is nothing but it is 100 into 500 mm. So what is this 100? 100 is your height, and this is your breadth, and this is your length. Okay, so which means there's a okay, this length, total length is 500 mm, and the breadth itself is 100 mm, and the height is 100 mm. Okay, so this thing I have modeled it in the Spaceclaim. Let me tell you all the dimensions, then only we can go into the modeling part. Okay, now one more thing they have mentioned in the paper here is that about the clear span. Okay, so here let me take the green part here. So they have mentioned, they have kept a platform here. Okay, they have kept a platform. This is a cylindrical platform. They have kept a cylindrical platform here. Okay, so they have kept a cylindrical platform, and they have mentioned here that the clear span will be the clear span will be 300 mm. Okay, so this will be 300 mm. So you have a spacing of here, so you have the offset, the end from the face, you have just 100 mm. Okay, just 100 mm with the entire thing. So just will not worry that thing, we'll just see that this has to be taken from 300 mm is the clear span. Okay, the clear span is 300 mm. And now we have the details. We need to get the details of the impact velocity. Okay, so the very important thing is impact velocity. Okay, the very important thing is, okay, very important thing is impact velocity. It is impact velocity. The velocity impact that is mentioned in this paper is 2.8 meters per second. Okay, it is 2.8 meters per second. We are going to load 2800 mm per second. Okay, so 2.8 meters per second is the impact velocity of the drop hammer. And the drop, one more thing that is to be is drop height. Okay, drop height is 400 mm. So this is 400 mm. Okay, so all those things I have mentioned here. And what is impact drop hammer is 4.5 kg. Impact weight, impactor weight. Okay, impactor weight is 4.54 kgs. And one more thing you have to take into account is the drop hammer. So the hammer is in this way. So I'm just drawing a very rough sketch here. So now the impactor is cylindrical impactor here. So this is an impactor. Okay, now let me give you the dimensions. So this is 180 mm in width. This is 180 mm in the width. So this is 180 mm. Now we have this, the depth is here, the depth here is 103 mm. Okay, 103 mm. Okay, and now we have a cylindrical diameter. So we have this dia is 30 mm dia. Okay, we have this as a 30 mm dia. Okay, so and you may also think what is the height of this projecting cylindrical impacting faces. It is also 30 mm. See, all those things you are getting in that paper. What I'm doing is I just mentioned in very brief thing that what is required for modeling actually. Okay, so what is required for modeling, and so let's go to the modeling part. So let me check here. Okay, let me go to the modeling part here. So in the modeling, already I have created the model here. Already I have created the model. So it's very simple to create the model, since it's just a normal beam, concrete beam here, and you can select, you can model it here. And while doing the pedestals, just while doing the pedestals, you can take a cylindrical part. You can take a cylinder and cut it half. Okay, you can cut it half. A cylindrical part, you can cut it half, no problems with that. Okay, so it's a no problems with that if you cut it half. And the impactor should be perpendicular. Okay, the impactor should be perpendicular to the longitudinal axis of the beam. The impactor should be perpendicular to the longitudinal axis of the beam. Okay, the impactor should be perpendicular. So which means there's a beam here. Your impactor, the longitudinal axis of the impactor is this one, XX, whereas your impactor should be perpendicular to this one. Okay, so in this way we are going to model it. We are already I've shown you the modeling part here. So modeling is not very difficult. Only thing is you have to ensure that the drop height is actually 400 mm. actually the drop height is 400 mm, but still I have taken the impactor very close to the beam here, so that actually the 400 impactor height is the drop height. Since I am giving the impact velocity directly in the Ansys workbench, then I need not consider the model to be very take 400 so I'll just show you while while modeling it in the mechanical part. So I'll just show you. This is one more thing regarding the material I'm just going to tell you is so material, what we have done, this is a structure, the two pedestals are structural steel, and the impactor also is a structural steel. That is a default material available in the Ansys. And the concrete beam what we have taken is just a plain concrete here. Just we are considering the plain concrete as of now, and then for the second result we are going to do it for the rubberized concrete. Okay, so guys, this is done, and now we are just going into the I have just taken the model. The model has been created here, and now let me show you the analysis that I have carried out. So I have carried out a lot of analysis here. So before getting into the things, we have to do some lot of analysis. So just to check whether the required result is obtained or no in that way. So I've already opened the model here. I've already carried out the analysis. Since this analysis will take a lot of time because it is having a repeated number of blows or impacts, so already I have done the analysis. I'm just showing you. I'll explain you how to define the boundary conditions and the loading pattern, and you can just try this. So regarding geometry, regarding connections, you can just see that there's an automatic connection, but still what I have done is the part, this entire impactor is getting contacted with the beam here. It's directly getting in contacted with the beam. So what I have done here is I have taken the impactor, the face of the cylindrical face of the impactor. I have created it as a contact body, and the target itself is the face, the top face of the beam. The top face of the beam itself is the target region, because the impactor will directly fall into that. And now I've made it as a frictionless, since there is no friction on the impactor and the concrete beam. And now we can see the meshing. So there's a meshing here that I have taken the default mesh. I have used a 5 mm meshing here. I've just used definitely I'm just used the 5 mm meshing. So I have used this because to just have a good results and the contours of the deflect analysis parts. So I've just used the 5 mm mesh, and you can go for a default mesh. That doesn't matter, but it actually matters on your efficiency. And now we have to insert this analysis is carried out in the Explicit Dynamics module. So very carefully you just see that it is carried out in the Explicit Dynamics, so that is very better. And now regarding the initial conditions, one very important thing is while initial conditions, you should just go and right click on the initial conditions and insert the drop height. Okay, you have to insert drop height. When you insert drop height, you get the following things that you need to take care. So the first thing is you need to select the body which is going to fall from a height. Okay, so the drop height test. And input type is input, means whatever you want to input. Here I'm going to input the drop height. I've input the drop height, which means the 400 mm that I have already told you. So the drop height is considered when you input the drop height 400 as a 400 mm, then automatically the software calculates the impact velocity by itself. Okay, there's an automatic calculation by itself which gives you a check that 400 mm is taken into the consideration. Okay, even though your impactor is very close to the concrete beam, it still has the 400 mm effect. Okay, so next thing, and don't worry about the pre-stress. Now the next thing is analysis settings. So just guys, just very carefully you just observe the analysis settings what we have given. I have given the number of steps to be 10, which means that entire time frame has been divided into 10 number of steps, and the current step number is 1, and the end time here I have given it as 0.001 sec. Okay, 0.001 seconds. So the time period should be short. Okay, so to ensure the results are correct. So since this is a very low impact test, and what I'm going to do here is just everything, and I have reduced the maximum number of cycles here. I have reduced the maximum number of cycles to get the results in a faster way. Okay, so in that way, so again nothing to worry much here. Only thing you can just do here is on material failure you can say it as yes, and the output controls you can say here it as 50. The equally spaced points are 50. You can just go for some 100. Okay, so it's not a problem. And next thing is fixed support. See, I have just given you the fixed support here. There's a fixed support here that I have mentioned. So the fixed supports are at below the pedestal, which means the pedestal don't move, they are fixed to the ground as it is given in the test here. So you can just see here in the test. So you can just analyze this part here, like how the setup is done, and the same should be carried out in Ansys as well. And now we are going to see one more support that I have given is I have taken the edges. I have connected the edges of the beams. You can just see that two edges of the beams have been connected to the pedestal. So this makes sure that the concrete beam is not moving. Okay, it's just not moving apart. So for this reason I have made it as a fixed support. And next thing is pressure. Very important thing that I need to tell you is the pressure here. I have given the pressure in a stepped way. Okay, I have given the pressure. The magnitude of the pressure is as like it will take the tabular data. I have changed my data here just by the time frame. With respect to the time frames, I am just changing the data here. Okay, I have just taken this as 0.63 megapascal. Okay, I have taken it as a 0.63 megapascal because I'll just tell you how it has been calculated. So I'll just tell you how it is being calculated. So guys, let me show you the calculations here. Let me take the red here. Okay, fine. Okay, so let me show you the calculations how I got the pressure as 0.63 megapascal. So let me tell you the pressure is 0.63 megapascal, which means the unit is Newton per millimeter square. I'll just tell you how we got the pressure. So what is pressure? Pressure is force upon area. Okay, I hope you know, and you will get you can just go cross check by the units itself. N Newton means it's force, and millimeter squares is the area. Force of resistance, force resisted. Okay, force resisted by area resisting the force. Force not it's not resisted, just take it as a force applied to the area resisted. Okay, so here the force applied here, I'm just telling you that it is 4.54 kg. So here in newtons, if you take it, it would be it would give you 45.4 newtons. Okay, it would give you 45.4 newtons. So here it is 45.4 newtons divided by area required. Here the area required would be the cylindrical part area. Just see here, just be very careful. This is the diameter of the cylindrical part here. This cylindrical part, this itself is the area resisting the pressure. Okay, so the area here will be cylindrical part, so it's actually circular part, pi by 4 into d square. So d is 30 square. Okay, so by this we will come into Newton per millimeter square. So by this you can arrive at 0.63 megapascal. Okay, this pressure has been applied continuously on the beam. So same thing, I have loaded it here. You can just correct here in the pressure and tabular data. And if you have already the tabular data in the Excel outside, you can just copy there from there and just mention it here. Okay, no problem. So after this thing, I've just calculated the solutions. I'll just show you the type of results. So I've calculated the solutions. If I just do the calculations now, it would take a lot of time. So to just reduce the your time and to get directly into the to the point, I have just carried out the analysis. So you can just see that 28.505. So let me probe the values here. Let me probe. Okay, so here you can just see the maximum principal stress that is occurring. So the maximum principal stress that occurs is 28.505 megapascal. So let me play the animation. So you can just see the animations here. So you can just see that animation here. So when the impactor is just impacting, when there is an impact on the beam, the red color portion and other things, you can just see here the load is getting transferred. You can see the bottom portion also. Here you can just see here there's a, since this is a freely supported, there's a direct impact on the beam, and hence the beam itself is getting moved a little bit. So let me show you the directional deformation. Okay, that's not very important here. So just see the maximum principal elastic strain here. You can just see the elastic strain here. So you can just see the type of load it has been impacting. So for the same thing, you understand, and we have elastic strain, maximum shear elastic strain here. So you can just see the shear load is also affecting the bottom of the beam. Okay, it's also affecting the bottom of the beam here. You can just see this part. And now we are going to see stick strain. Okay, now maximum shear stress. Okay, you can just see the maximum shear stress here. You can just see the maximum shear stress. So for the same thing, we are going to analyze the cracks, okay, later in the next video. So stress intensity, you can just see the stress intensity. And the shear stress, you're going to see it absolutely very fine. So the shear stress is also being transferred into the bottom of the beam. So you can just definitely see here there's a maximum shear stress for the load and normal stress. You can just see the normal stress here. And now we have the vector principal stress. Okay, there's a vector principal stress. So this is a principal stress. This is not a maximum principal or minimum principal. It's a vector principal, which means that it will take the effect of both I, Z, and I, Y, and Z planes. So in this way, this is a vector principal stress. So just has not so very much important. So energy probe, we are going to see the energy probe here. So that you don't get any results here, but we get a good graph here. So the energy we get here is the energy probe. This is the energy probe that we are getting. So for the times 1.7 seconds, we have the energy probe as 0 millijoules, and for add this load, okay, at the load of 4 points, this load, we have the energy as 49.867 millijoules. So you can just see this, just remember this value, that's a 49,867 millijoules here. And now we can just see here 48. So just show you the impact energy for the first three parameters. So you can just see that almost the same value I have got here. You can just see that the first crack here is a 48.1 megapascal. So the same thing can be validated in my Ansys validation. This is not very very accurate, but still you can just see that at the 49,498.6.7, this is millijoules. Okay, this is a millijoules. Okay, so it's a millijoules, and we can just see that this in the paper, that this is a joules, it's in a joules. So 48.1 joules of energy for the 3 number of impacts or first number of blows. So still a lot of things, since the paper is very in detail, and they have carried out the analysis for lot of loads, and this one that cannot be done in the video here, because it takes a very long time, and some people might get bored here. So again, the last thing is strain probe. Okay, initially the strain is not so so for the 0 second and 1:0, 2 into e⁻⁴, the strain is absolutely 0. So when the impactor impacts the strain, then the strain it goes on increasing, and it still increases. Okay, so one important thing I need to show you guys is the chart. Okay, so the chart that I have got here is the maximum principal elastic strain versus the time. So this is a graph here, and the one more graph I have got is the strain here, directional deformation versus the time, and the third one here is the most important thing, that is a normalized pressure and pressure intensity, and whatever pressure I have given, and the pressure intensity. So based on this we have calculated. So guys, I think you have understood the type of analysis to be done. So this will be same thing that will be repeated for the rubberized concrete. You need to just model it in the Ansys module. You have to create a material specific to this experimental data. You have to create the material, and then you have to load here. So according to this, I hope this you have understood this video. So please do like my video, share it to your friends, and subscribe to my channel. So please make me a favor, because this type of videos you don't get a very good detailed video is in the YouTube. My only intention is to make this video viral, and make students understand the concept and the importance of Ansys validation. And since I've helped many students in MTech projects, so for them this would be a very good gift for them, or that it would be a very important thing to them, for them to just get some idea on what they are working on. It's not like they have to work on the same thing. They get some idea or some points that I have mentioned in my video, and that would be helpful for them to continue their journey Okay, so guys, thank you, have a good day.